Go. Hello, Mr. Eric, Mr. Ryan, are you right? Yeah? Today is Christmas Eve, okay? So yesterday we talked about directed acyclic graph and the topology sorting. Right? Topology sorting with regarding to DAG, directed acyclic graph, is that, for example, given this directed acyclic graph, A points to B, B points to C. That's the dependency. Look, in order to visit the node B, we have to visit A first. In order to finish C, visit C, we have to visit B. And the order will be A, B, C. That's the only way to visit all the nodes, right? And yesterday, what are we talking? What did we talk about yesterday? Topology sort. Yeah, yesterday we talked about. We haven't actually talked about sorting yet, but we talked about where to start the visiting the nodes. For example, here, how do we do it?
Because if it does have in grade or something like that.
Integrate, yeah, we integrate. We check the integrate. If it integrate is the number of edges points to the vertex. Yeah, for this one, B integrate is 1. Out degree is the going out of the vertex is 1. So we compute, iterate the edges. Yeah, iterate over the edges, and we updated the integrate, and then again we go through the vertex again, and then we find out a collection of the vertex which has the integrate equals 0, means that there's no dependency, there's no edges pointing to it. It means there's no dependency. We can start it right away, right? Yesterday we were talking about to find the minimum nodes starting visiting the graph, okay? And we use the integrate, and then GB means that to update the integrate B, because the edge A points to B, and then B integrate needs to be incremented by 1. And then we go through the edges nodes again, and if the integrate is 0, we can put it in the starting node list, okay? The time complexity is not ON, actually it's ON plus M, yeah? To be more precise. N is the number of nodes. Yeah, roughly, yeah. And, okay, so look, we are visiting the edges. This is edge here. So this is OM if there is n number of edges. And then the next loop will be visiting the nodes. There will be n nodes. Okay, so OM plus M, right? Or you can say O max n m, okay? Sometimes you can write it this way, right? So look, the first step, iterating over the edges. The second step, iterating over the nodes. The time space complexity, we're using the nodes. That's ON. What's this? These, yeah, ON. So the space complexity is ON, okay? Okay, yeah? Given there are n vertex, for example, given there are n vertex, what's the maximum number of the edges for this n vertex if they are simple, if this is a simple graph? Remember, yesterday we talked about simple graph. Yeah, this is the simple graph.
Simple graph.
But this is not, yeah? Yeah, because there are multiple edges. No, look, two nodes, there are 1 edges. 3 nodes, 3 edges. 4 nodes, how many can you get?
4.
How about these 2? 6. And 5 nodes, how many edges can you get? Look, this is the complete graph, yeah? But again, I have added 1 more edges, adding 1 more vertex. So what happened? I can have 1 more edges to the previous n nodes, right? Yeah? Make sense? Do you get it?
It looks like a ditto.
So how do we get it? Look, how do we get it? When we have one vertex, what's the number of edges? 0. 2 vertex? 1. I have points to the previous one. Yeah, plus 1, right? So that's plus 1. So I have another vertex here. So how many edges I added? Plus what?
Plus
2. And I have, look, this is 3 vertex. I added 1 more vertex. How many edges I can have? Plus what?
3.
Yeah, exactly. So look, I have n vertex. I don't know how many you got, yeah? But I added 1 more edges. 1 more vertex, I can have n more edges, right? So the answer will be what? The answer will be what? This is number of vertex, yeah? Look, 0, 0, that's 1, like 3, yeah? 1, 3, and then what's next? 1 plus 2, 3 plus 3, 6, yeah? Look, so it's n minus 1, n times n minus 1, yeah? Divided by 2. Am I right? Let's put it 0 is 0. 1 is still 0. That's not right. Okay, 1 yeah, 1 is 0, yeah, that's right. 2 times 1, yeah. 3 times 2 divided by 2 is 3. That's right. 4 vertex. 4 times 3 divided by 2, 6 edges. It's right, yeah? Do you see how we're getting this? Yeah? Yeah? Make sense? Look, plus 1, plus 2, plus 3, plus 4, plus 5. Right? It's like the number of what? Yeah, it's quite similar to the number of the sublists for n size list. Am I right? Okay, so look, the topology sorting is the order. Yeah, how can we get this? Yeah, how can we get this? Look, this part is putting all the nodes. Putting all the nodes here. Yeah, answer is the number of nodes we can start. Okay. How about if I change this to DQ, right? And if I said DQ, what's in your mind? What kind of algorithm is associated with DQ?
Double-ended key.
Yeah, I know. What kind of breadth search? Yeah, breadth search is okay. Okay, so this DQ, yeah. So how about I put it in the DQ, right? And then I do this breadth search, right? Yeah, and what happened? So I need to update it. I need to update it during, when I do the traversal, right? Okay. So this will be the same, okay? Answer, yeah. This will be the same, so I don't write it, okay? And then now what? Let's say put in a Q. What?
Nothing.
PQ. Q dot append n, yeah. Q dot append n. And then now I can do this wire Q, right? Wire Q. What? 4. This is 4. Okay, come on. Do you want to finish this quicker? Come on. Wire Q. So, what's the first step to do the breadth search?
Q dot pop.
So I have this current dot Q dot pop left, yeah? Now, okay, so there's one thing missing. Yeah, because look, I have this dependency, but I need to remember which nodes, yeah, which nodes coming out of it, right? So we have to integrate, yeah, but we also have to remember the nodes that coming out of it. Make sense? Why is that? Because look, yeah, look, A to B, this is C, yeah? In order to finish C, right? Yeah? In order to finish it, I have to finish A and B first, right? Yeah? If I finish A and finish B, and then I possibly can start with C, am I right? Yeah? So, look, there's the information. Look, I have this I need to remember a node's out degree. So I need to look GB equals A, and then I need to have a node. Node will be also default dictionary, which is the list of integer, right? So the node A points to B, so I need to node A plus append B, right? Yeah. So look, A will point to the, so I can use this information to see how many edges coming from A, right? And how many edges coming to B, so I can just use the n, right? So look, I currently get a node C, and then I need to for A in node C, right? So this is A is the node coming from the C, okay? Yeah? Okay, I will ask you a question later. You need to listen carefully, okay? Node C. What's node C?
Node C is the thing that comes in from the...
In or out? In or out? Look, GB.
Out.
Yeah, GB. Look, this is A to B, right? B is the integrate. A points to B. Yeah. Okay, yeah. A, B, and edges. A points to B. B integrate plus equal 1. A knows A plus equal B. Well, what's this mean? What's this mean? What's here? What's this mean?
You think that
No, it's the default dictionary list type is list in, okay? It's the same. It's the same type, okay? Node A, it means the A has one more edges coming out of A to B, right? Yeah? So I go through this, it means that I iterate all the edges from coming out of C. And if I coming out of C, what happened? Look, this is C, yeah? I'm currently at C, right? And then this points to A, right?
and
Okay.
smiley face.
Okay, look. C go to A, right? And then now, C is the number, is current one. And then C needs to put, if I finish C, then I need to do what? I need to do what for this one? I need to do what?
A.
So look, I remove one dependency from C, from A, from A. C is the dependency of A, points to A. And now I visit C. So it means that this dependency, this integrate should be what? Increment or my decrement?
Integrate increment.
No, I have this already. I have calculated this plus 1 equal already. And now I visit C already. So what should I do with? Sorry?
Decrement.
Decrement, exactly, because I already visited C. So look, there's one less thing to do. In order to, there might be another one called D. Yeah? Look, to finish A, you need to put the C and D first, right?
C and D and smiley face.
Yeah?
You forgot smiley face.
Come on.
No, you didn't.
Yeah, I know. So look, I have to
You
do what?
didn't.
G what? A minus equals 1, right? This is integrate minus 1, right? Because we already visited 1C, so that's one less thing to worry about. Yeah? And look, if this integrate becomes 0, what happens? What should we do? If this already, if I minus 1 here, and then it minus 1, so what happened? What happened to this A?
You only have a smiley face.
Come on, listen carefully.
Yeah.
If I look at A, if I visit C and visit D, so what happened to A? The integrate will become what?
0.
So what happened in this case? If we integrate 0, what should we do now? We can visit it, right? So what should we do with the Q? What should we do?
You can put it.
Put it in the Q. Yeah, well done. Look, if G A equals 0, then we can put it in the Q, right? Because look, A is free now, right? We already finished C and D, minus 1, and then we can just say Q dot append what? Append A, right? Because we visit A, right? Yeah. Look, the order coming out for top left. This is the topology sorting. Yeah. Make sense? So what's the topology sorting? What's the algorithm we're talking about here?
Okay. So
What? What's the topology sorting? Yeah.
the topology sorting is just finding the integrate.
Not the indigo. I mean,
the 0.
so I have another graph here. So you tell me, can you tell me one of the topology sorting? You know the topology sorting might be different. There might be a different. You just give me one of them, alright? Yeah. Points to C, and then D here points to C, points to E. Okay. Okay, so what's the topology sorting of this graph? Come on. Any. It does, come on. A, yeah?
Yeah.
A, and then what's next?
B.
B, yeah? And then
D.
D, yeah?
C.
C. Well done. This is one of the topology. Can you find another one which is also okay? Which one? Sorry? Which one is also okay?
A.
Yeah? A? It's the same. I mean, can you look? I give you a hint. What's this D? Can we swap with D and A? I mean, can we start with D
Oh
first?
yeah.
Yeah, because it's independent. Yeah, D, and then you do what? A. You finish A, then you can finish B and C, right? B, C, and then E. Okay, so this is also okay. There are two topology sorting. Okay, yeah,
The key.
makes sense. Yeah.
The key.
And look, we use the Q. First of all, so for the topology sorting, what are the initial nodes? What should we put to the Q first?
The starting node that had the in degree of 0.
Well done, you're listening, yes. Individual. And then, once we visit, we take it, this is the kind of like BFS search. Look, Q equals, C equals Q the top left. So we take one from the Q, and then what should we do here? What's this? What should we do here?
We
So we take one out. Look, we take for.
one out, and then if in degree is 0, then you just put it into the queue.
Okay, so for example, I take the C out. Yeah. Look, C can be started. I take it out. So what should I do with next?
You should do
What's this NC?
D.
What's NC? What's NC means? What's NC here?
NC means the out degree.
The number of the edges, the vertex that points from the C, yeah? So look, NC will be A, yeah? Yeah? Yeah, NC will be A, right? Because there's A vertex coming out of C, NC. And then I go through the out nodes, right? Out nodes. And then, look, because I'm visiting the C already, so it means that A has one less dependency, right? One less dependency, and then I need to decrement the integrate -1. And when this A is integrate means 0, what does it mean?
Means you can put it in the queue.
Yeah, why is that?
Because the in degree is 0.
It's 0 means that all is what? All is prerequisite. Yeah, prerequisite. How do you pronounce that word? The thing that depends on A. Yeah. All the thing that depends on A, like C, D, or whatever, there's another E here. All the integrate, all the edges going to A, C, D, E, these dependency have been visited. So it means that I can visit A now. So when I want to visit it, I can put it back to the queue, right? So the number of edges, look at the number of edges. Whenever we find out whenever we decrement the edges, yeah, then we can have this in r plus equals 1, r equals 0, right? And then at the end, we just check if this r equals the number of edges in this graph. If it's equals to the number of edges in the graph, what does it mean? Right? Look, I have for example, I have 3 edges here, right? And every time I decrement one dependency, I plus equals 1. And I check this r if it's equals to the total number of edges. If it's equal to the total number of edges, it means that I can visit all the nodes in this graph, right? Right? Make sense? If this r is not incremented to the total edges, it means that I cannot, right? Let's take an example like just simple example, yeah. B, C. Okay, look this graph, yeah, we count, right? Okay. So look, so maybe we put another one, D, yeah. So the starting node will be only D, right? In the queue, right? Yeah, right. So there are how many edges? 1, 2, 3, 4. 4 edges. 4 edges. Yeah, 4 edges. The starting point will be D. So I take D out. Right? I take a D out. What is our degree? A. Right? So I increment GA minus 1. Look, what's the degree of A here?
G.
What's the degree of A?
G.
No, what's the number of degree?
1.
How is the 1?
Only 2.
2, right? Look, 2. So I only increment 1, so it's 1 already, right? And then the next time the queue is empty, and then it just clicked. So R will be only 1. We're only able to remove 1 edges, right? And that's it. How many edges we have got? 4 edges. What does it mean? if r is not equals to total number of edges, right? Or we can say r is the number of edges and r minus equals 1. If r is not 0, so what does it mean?
R is not 0, then
Look, r is at the beginning equals 4, okay? And then I look, every time I remove our dependency, I remove 1. R minus equals 1. R will be 3 now. So what happened?
If it will be 0, then you can do...
I can visit all the nodes, right? If it's not 0, it means I cannot visit all the nodes, alright? Yeah? This is topology sorting based on breadth search. It's similar to breadth search, yeah? The only difference, okay, so today's takeaway, the only difference is what? With the breadth search, you know the level by level, right? Level by level. We use the Q, DQ, yeah? Push to the right, append, pop left, yeah? Take one out or take everything out, right? The difference is what? We push the nodes with in degree equals 0 to the Q, and we decrement the out degree, the edges coming out of it. Look, this is current node, and then there are many nodes pointing out, yeah? And then I need to decrement the in degree for this, right? For the nodes that coming out of it. And once the in degree is 0, then we push it back to the Q. Exactly. And then order of taking out the nodes from the queue is called topology sorting. This is useful. For example, I give you a list of tasks that has dependency, and then you need to tell me the sequence, right? A, B, C, yeah? Play piano, do homework, and then do what, and then playing game, right? You need to plan, make a plan. This is topology sorting. Helps you to do the plan. Okay? Yeah? And then you also can tell us that if we can visit all the nodes in a directed acyclic graph, okay? Acyclic means that it's not impossible, right? Make sense? Yeah? You see, this is really useful, right? Do you see it's useful? Yeah? Okay, that's it for today. Good job.
Bye.
Bye.